Welcome to This Explainer. Today, we are going to unpack a seriously fascinating weekend experiment. We're looking at the harsh realities of trying to run an autonomous coding agent entirely locally on your own hardware, and more importantly, why it didn't quite go as planned. If you've ever daydreamed about ditching the cloud entirely for your AI coding tasks, well, you're definitely going to want to pay close attention to this one.
Let's kick things off with a quote directly from the author of our source material. They said, "I wanted this to work badly enough that I spent a weekend on it. It mostly didn't." I mean, talk about relatable, right? That perfectly captures the allure, the ambition, and ultimately the utter frustration of trying to replace a massive hosted AI with a local one. The failure itself is interesting, but as we'll see, the underlying mechanical reasons for why it failed are absolutely fascinating.
Section 1. The seductive local pitch. To understand why anyone would even attempt this experiment in the first place, we really have to look at the pitch play. Free, local, zero API bills. It's incredibly seductive, and it's driven by three core benefits. First up, cost predictability. When you use a hosted agent, it's constantly reading and rewriting your codebase, meaning your API bill scales with every single token. Locally, it's just a flat electricity bill. Second is data locality. Your code literally never leaves the machine. If you're working a client contract with a super strict data residency clause, this is a massive win. And third, just plain curiosity. Open-weight models are genuinely getting so good that asking if they can replace a hosted model is now a serious engineering question, not just a joke.
Section 2. The chat versus agent trap.
Look, on paper, connecting an agent like Claude Code to a local Qwen model is frankly trivial. You just point the base URL at Ollama's OpenAI compatible endpoint, pull your Qwen checkpoint, and boom, you are up and running. The agent sends requests, tokens come back, 20 minutes, and you're totally done. Honestly, if all you wanted was a standard AI chat window that just answers your coding questions, you could stop right here and call it a massive victory.
But here is the trap, and this brilliantly illustrates the difference. A chat window is forgiving, right? It just answers your questions. If it formats something slightly weird, you figure it out. But Claude Code was never meant to be a simple chat window. It's an agent loop, and an agent loop is entirely unforgiving. The exact moment the agent tries to actually do something, like read a file, run a shell command, or apply a code diff, the rules of engagement completely change, and that beautiful local setup just starts to crumble.
Let's break down the actual mechanics of that agent loop to see why. The model doesn't just give you an answer, it decides which tool to call. It emits a strictly structured call for that tool. It waits for the result, and then it decides what to do next. It repeats this cycle entirely autonomously. There's no human sitting there checking each individual step to make sure it makes sense.
Which brings us to Section 3. Why the loop breaks.
So, because this autonomous loop requires absolute perfection, the true bottleneck here isn't actually the raw intelligence of your local model. It's tool call formatting. The loop only survives if the model's tool calls are syntactically correct every single time. Hosted models from companies like Anthropic are trained incredibly hard on this exact behavior. It's not some clever prompt trick, it's a fundamental property baked right into their weights. But smaller open-weight models, they only approximate it. And approximate, well, that's a fatal flaw for an autonomous loop.
During this weekend experiment, the author slammed into three very specific, highly reproducible failure modes where that approximate formatting caused the entire system to crash. Let's walk through exactly what these look like in the trenches.
Failure mode number 1, malformed JSON. We're talking about tiny things, a trailing comma, an unescaped quote inside a file path, an unclosed string. Now, what's really interesting here is that if you had a human pair programmer sitting right next to you, their brain would mentally autocorrect a trailing comma without even noticing it. But a strict JSON parser? No way. It rejects it outright. Turn killed, instantly.
The second failure is what the author calls prose wrapping. Instead of just emitting the clean, structured JSON call that the machine needs, the model gets, well, a little too chatty. It narrates its intentions in natural language around the JSON block, literally explaining what it's about to do. The agent's strict parser has no reliable way to strip out that friendly little framing, so it just gets confused, throws its hands up, and fails.
And this third one is honestly the most fascinating failure mode of all. Schema drift under long context. Formatting actually held up totally fine for the first few tool calls. But as the session continued and the context window filled up with prior tool results and file contents, the model literally started to forget the rules. Its adherence to the exact formatting schema degraded. And it didn't just degrade randomly, it got predictably worse the longer the session ran. So you really have to picture this agent loop as a highly, highly fragile chain. It has absolutely zero tolerance for approximate formats. Remember, unlike a human pair programmer, the model cannot notice its own typo and say, "Oops, let me fix that," mid-sentence. The parser has already thrown a hard error and crashed the session before anyone could even step in to correct it. One weak link, and it halts the whole shebang.
Section 4. 3 paths to fix it.
Because this isn't an issue you can just wave away with a simple configuration flag or a quick prompt tweak, there are 3 honest engineering paths forward to make local models actually work for this kind of agentic loop. But, fair warning, each comes with heavy trade-offs. The first path is to fine-tune the model specifically on the exact tool call format. This is the do-it-properly option, but obviously it requires expensive compute and a whole lot of time. The second is building a repair layer, a strict validator sitting right between the model and the parser just to catch and patch those trailing commas or prose wrappers. But that is a heavy engineering project, definitely not something you just bolt on in an afternoon. The third option is to simply scope down the agent's autonomy. You limit it to read-only or single-step tasks where a slip-up isn't fatal. But of course, doing that completely sacrifices the autonomous magic you wanted in the first place.
Finally, Section 5, the ultimate takeaway. To distill what this experiment actually teaches us, we have to realize that run your coding agent locally and run a local model sound like the exact same claim, but this experiment proves they are wildly different beasts. The real gap isn't raw model intelligence. The author clearly notes that Qwen is genuinely capable at writing and reasoning about code, but it simply wasn't trained to be the deterministic half of an unsupervised agent loop. That highly specific training for tool call reliability, not parameter counts and not benchmark scores, turned out to be the entire ballgame. So I'm going to leave you with this final, somewhat provocative thought. If you are evaluating local models for agentic coding work, you are asking the wrong question if you just ask, how good is this model? Instead, the critical question you absolutely must ask is, how good is this model at never breaking format? Because in the unforgiving world of autonomous agents, formatting discipline is the only thing standing between a truly useful tool and a broken weekend demo. Thanks for